Hello, everybody. Anyway, welcome to this Collaborate session. So I'm running it this week. Zelani will do next week's one on the content. So basically, I'm here to talk about the week 5 content. And there's really two things, non-parametric tests, which are things like the Wilcoxon test and the Kruskal-Wallis test, and the chi-squared tests. And so kind of do those separately. So the way I intend to proceed is give a few slides, a little bit of theory, and then go into R and demonstrate. I won't demonstrate everything, but hopefully give you a bit of a feel for how the non-parametric tests are different to the parametric tests. Okay, so let's get started. So what are they? Basically, they're tests where we're not assuming things come originally from a normal distribution. And they're called non-parametric because they don't assume a distribution with parameters. So normally, a normal distribution will have a mean and standard deviation, same as a t-distribution. So these tests don't require that. What they're suitable for are really highly skewed distributions, or distributions with extreme outliers. And the reason for that is that if you've got enough data, your data set's not too small, then if you have a non-normal data, your sampling distribution will be approximately normal by the central limit theorem. So if you've got like about 30 category, you can assume that by the central limit theorem, you can normally assume that the sampling distribution is normal. And that's what most of these parametric tests like the t-test and the ANOVA assume. So again, you usually test to see if your data is normal. But you then, if it's not, and you've got enough data, you appeal to the central limit theorem. If you don't have enough data and your data is normal, at least you can see that it's normal. If you've only got about 5 data points, then it's difficult to tell whether it's normal or not. But if you've got a reasonable number and it looks normal, then it's also true that the central limit theorem basically says if you start with a normal distribution, the sampling distribution will also be normal. So that's why we test the sample to see that it's a normal distribution. And if it's not, we don't worry overly much, but something that can really screw it up, the central limit theorem that is when we have extreme outliers. I don't just mean something that's kind of like just outside the whiskers of the box plot, but something that's a fair way away. And if you think about it, with a lot of those t-tests and things, if you think about the sampling distribution, then if you've got an extreme outlier, then you're taking lots of samples. Sometimes the samples will include that outlier and sometimes they won't. And therefore, because the mean is very sensitive to outliers, then there's no way that you're going to get a normal distribution for your sampling distribution. So that's kind of why it works. Anyway, that's kind of about parametric tests as a bit of background. There are these things called non-parametric tests, like the Wilcoxon and the Kruskal-Wallis, and they don't make the same assumptions. They don't assume a normal sampling distribution. So one question is, why don't we use them all the time? And I'll explain that. Because, yeah, if they're more robust, then why not just always use a non-parametric distribution? There's a reason that we don't. And that reason is because they have less power than the parametric tests. What that means is that they're If there is actually a significant difference, then they're less likely to pick it up than what a parametric test would if the assumptions were satisfied. So it would be silly to use a non-parametric test on something that satisfies the assumptions for a parametric test. You would only use it if the assumptions are violated. Now, why are they less powerful? Without going into really deep reasons, it's because these non-parametric tests use the ranks instead of the numbers. What that means is, although the notes don't go into a lot of detail about how to do them, to perform these tests manually, what you would do is you would take your data and then you'd sort it from, say, maximum to minimum or minimum to maximum. And then you would say, take each data point and you would give it a rank. So the highest, the largest one would be rank 1, the second largest rank 2, third one rank 3. So you're sort of throwing away a lot of information about, like how far apart your data points are. So that's why it's not as powerful, but it doesn't rely on the assumptions as much. The other thing you can do with these non-parametric tests that isn't mentioned in the notes is that because they work with ranks rather than numbers, you can actually use them if you have ordinal response data. So if you've done a survey with a standard Likert scale, some people think that you should be using a non-parametric test purely for that reason. Not everybody thinks that. Quite a lot of people just convert them into numbers and merrily go ahead and analyse it. But purists like to think that you shouldn't use a parametric test on survey data. You should use these non-parametric tests. But anyway, that's kind of a philosophical argument, but I'm just making that point that you can use them in place of the parametric test because they use ranks, which is ordinal data rather than continuous data. Am I a purist? I think I'd like to be, but I'm not. I'm a bit more pragmatic. So if you're asking me if I'm marking an assignment that did a survey and they did a parametric test, I wouldn't be marking it down. I would like them to explain that it's a limitation, that's what they've done, but I wouldn't say it's wrong because it's accepted practice. I hope that kind of answers your question. If I was doing it myself, yeah, I probably would. But, in terms of marking, if something's accepted practice, then that's fine. I think Yvette's more a pragmatist, that she would be happy to use a parametric test for a survey. Okay, so what do? They test for differences in medians rather than differences in means. If you're talking about the equivalent of a t-test, which is a Wilcoxon test. So instead of testing whether the means are different, they test whether the medians are different. And that's another reason that makes them more robust to the presence of extreme outliers, because medians are not affected as much by extreme outliers as what means are. So in other words, if you take a data set and you calculate the mean of it, and then you added an extreme outlier, mean is going to shift a lot. But the median isn't. It may not change by very much at all, if anything. So the medians aren't sensitive to extreme outliers. Okay, so the Wilcoxon tests are equivalent to the t-tests, and the Kruskal-Wallis test is equivalent to ANOVA. That's pretty much all you need to know, other than how to use it, which is what I'm going to demonstrate, at least for the Wilcoxon test. George, do you mind not kind of interrupting what I'm talking about? Oh, sorry, hang on. I haven't read all your... let me apologise for that. I just should read everything you wrote. Okay. For the quiz, you need to understand the manual way to calculate the test where it's done in the notes. So if the notes don't... I can't remember if the notes go through calculating the Wilcoxon test by first principle, but they certainly do the t-test and the ANOVA. Okay, so then if it's not in the notes, it's not going to be in the quiz. Yeah, I mean, I think it'd be nice to teach how to do it manually, but there's just not enough time. We're kind of a bit too pressed in 6 weeks getting through everything. But anyway, you can easily, at some later stage, you can easily find it yourself if you wish to know. Okay, this is just a quick comparison table. So there's something called the Wilcoxon signed rank test. That tests whether the median is some known median, and that's basically equivalent to a one sample t-test. The Wilcoxon two sample, that's basically the two sample t-test. There's a matched pairs Wilcoxon corresponding to the paired sample t-test, and there's the Kruskal-Wallis, which tests that all the medians are equal, and that's equivalent to the ANOVA. So it's quite easy. There's just a direct equivalent non-parametric test for each parametric test that you've learned. Okay. I think there's even non-parametric regression tests, but we don't cover those at all. There are later next week when we're doing correlation, you'll see there's some non-parametric versions of the basic correlation test as well. But you'll learn about that next week. Daniel said, "Is it better to do data transformation than do a non-parametric test?" In my opinion, no. Data transformations, in my experience, rarely work well. And while they might fix up one problem, they then create other problems. Like, okay, so Karen asked if I can repeat the description of the first two rows. So the Wilcoxon signed rank test, which is equivalent to the one sample t-test, that tests if a median is some known median. Just like the one sample t-test tests whether the mean of your sample is the same as the known mean of a population. The Wilcoxon 2 sample, basically the null hypothesis for that is that the medians are equal. And that's the same as similar to the two sample t-test or the two independent sample t-test, which the null hypothesis tests if the two means are equal. So I'm talking about the null hypothesis here. Okay, the R functions are Wilcox.test and Kruskal.test, so they're easy to remember. Main assumptions are data from a simple random sample and response variable that's continuous. Actually, I don't quite agree with that second one because they can be used with ordinal data. So I might fix up that slide, but I think that's what the notes say, but I think it's not quite correct to say that. Right, so that's kind of my quick overview of the standard non-parametric tests. What I intend to do now is an example using R of the Wilcoxon two sample test. So just check if anyone has any questions, and then while I'm doing that, I'll just set up my R. So I'll be with you in a second. As soon as I get this set up, before I get into it, I'll answer any questions. Okay, so First, I'll answer Kelly's question. So if you have an outlier, but without that outlier it is normal, would you use it non-parametric? Yeah, absolutely. Yeah, if it didn't, if yeah, I would use a non-parametric. Unless you've got some reason to remove the outlier, I would be using a non-parametric. And then the second part of that was that the mean is the only one that is significantly affected. Yeah, I'm not sure about whether the variant, I think the variance would be affected as well. But it's mainly because the mean's affected. So I hope that answers your question. And then I'll get on to Daniel's question. So is my data more or less accurate if I transform the data and do a non-parametric test compared to a I think you meant compared to a parametric test. Yeah. Okay. Is my data, no, it's actually not your data being more or less accurate. Your data is your data. I'll say if you transform it. I don't really quite know what you're getting at. If you transformed it, and you found that it was normal with no outliers, then I'd be using a parametric test. If you transformed it and then found that there's still an outlier there and you're forced to use a non-parametric, I would go back to the original data. I wouldn't use the transformed data. So I don't know if that's what you're asking, Daniel. But I hope that makes sense to people anyway. But yeah, I mean, yeah, I tend to, just me personally, I tend to use transformations as a last resort. But yeah. Okay, but does a transform test, there's no such thing as a transform test. Transport, you pointed out, yeah. Does transform data tell you exactly the same thing as the original data? Well, not exactly. Suppose, for example, you did a square root transformation, then what that, and you did say a parametric test, like a t-test with two samples, then what that's telling you is that the square root of the means are different. Okay, now from that you might deduce, okay, well, the square root of the means is significantly different, therefore the means are significantly different. But if you've done a square root, it's telling you about the square root. Sorry, not even the square root of your means, it's the means of your square rooted data. So I find that when you do a transformation that the interpretability becomes much harder, which is why I don't like it as much. But you know, you've got to make your own judgments about that, particularly for your own data. So generally speaking, if it were me, again, it depends on the data, but if it were me, I'd be looking to do a non-parametric test first, and then maybe before transforming it. But then accepting that your non-parametric test is going to be less powerful than a parametric. So you'd probably do both and then, yeah, see what you conclude. But yeah, I don't know. What I would it's just the difficulty interpreting transform data that I don't like so much. So there's no really direct answer to that because it depends on your data. But just as a kind of general principle, more than as a specific thing. Okay, so you guys ready to see some R? Looks like maybe one question. Okay, all good. So, all right, so let's do that. Still got the slides up there, so I have to switch screens. Okay, just take a peek behind, and yep, my R's there, but it's kind of annoying because I can't see enough. But if I make it too big, I can't see your comments, so it's a bit kind of awkward. But yeah, I should have made the font smaller, but then you wouldn't be able to read it. So there's no great answer. Yeah, just have to manage, I guess. Okay, so what I'm going to do is, for some reason, I like this data set. So I'm going to look at the birth weight data set that I've referred to before. That's also mentioned in the notes in week 4. And I'm going to look at that. I've just renamed it as week 5 so I can tell what's what. So I'm going to read that in. But before I do that, I'm also going to load up a package called the car package. My reason for doing that is it's got a really nice QQ plot command that I like a lot better than the standard one. But you don't have to use that, but you'll see when we get to it. We're going to do some QQ plots. Okay, so let's do both of those. And it looks like I've set that up. I've got a data file there, which I've been called just simple D, just a bit slack, but just because I don't want to type it out all the time. And that's my data set, if you remember it. They had various variables, low, that's just an indicator of low birth weight or not, age, mother's birth weight, race, which is the ethnicity, that 1, 2, or 3, and smoke. This is the one I'm interested in, is whether the mother was a smoker or not, and lots of other things don't tell you much. And then the other key variable is the birth weight. And it's a numerical variable that's in the range of 700 to 4,990. So that's the birth weight in grams of the babies. Okay, so that's a quick look at the data. Okay, oops, what have I done? I think I've accidentally deleted a whole lot of stuff, have I? Yeah, that's all right. Maybe not. Okay, next line. I'm maybe just lazy. I'm going to store birth weight as a single vector. I don't really need to do that, but just something I prefer to do. Oh, now I've lost it again. Okay, so what I'm going to do is I want to compare the 2-sample Wilcoxon test against the 2-sample t-test, just to see what the difference is. Okay, what I'm going to do here is I'm going to make smoke a factor. Turns out I need to do that for the smoke variable when I use the non-parametric test, otherwise it gives me an error. Just 1 second, I've got to plug my power into my laptop, otherwise I'm going to run out of power suddenly. Okay. So I did that. And what I'm going to do is I'm going to make a box plot. That's usually the first thing. You can see my 2 box plots here. They're not terribly great, and part of the reason for that, I think, is because I've used a really big label. So I'm just going to cancel that so I can get a better view of it now anyway. Or what I'll do is I'll just zoom it, but I don't think you can see that if I do that. No, it doesn't show up on your screen, so I can't zoom it. So let me just get rid of that label. I didn't do it. Okay. Why is that? Maybe I need to fiddle around with the margins. fine when I did it before, but because I've resized all my screen and everything, okay, let me do this. I'm just going to change the margins. That's better. Now at least you get a bit of a picture of the box plot on the right there. So what do we notice about this box plot? So looking at the smokers and non-smokers, does it look like they're different? What do you think? Yeah, pretty good. Yeah, so observed all the things I was going to suggest. Right, so smokers have a significant outlier, that's true. The other ones, the non-smokers don't have outliers, but the smokers certainly do. Medians are about the same. Our tests, our normal t-test is on the means, not the medians, but still you get kind of picture of things by looking at a box plot. There's a little bit of a difference, slightly lower. Variance looks about the same to me, I agree. Yeah, so I'm pretty happy to use the standard t-test rather than the Welsh t-test. So I'm happy to, in the t-test, to put in that the var dot, anyway, the variance is equal. Variance is a measure of spread of the data. The box plot gives you IQR, which is another measure of spread. So, yeah, so it's not really accurate. It's not really precise to say that the variances are equal, but they're probably pretty close. Now, you can work out the variances of both data sets if you want to be a bit more careful about that. There's a kind of rule of thumb that says if the variances, I think it's the variances of one group is more than 4 times the variance of the other, then we consider the variances to be not equal. But if it's within a factor of 4, we're probably happy. Or in other words, actually, when I say variance, yeah, also remember that I said something that was not quite right there. The IQR is a measure of spread, and so is the standard deviation. The variance is the square of the standard deviation, so it's the standard deviations are roughly similar, then it means the variances are roughly similar. But the rule of thumb is that if it's within a factor of 2, even for the actual standard deviations, then we would say that that has equal variance. If it's more than a factor of 2 per way, then we say it wouldn't be. So that's kind of a rule of thumb. There are various tests for equality of variance, such as the Levene test and things like that, but we don't teach that in the course. Yeah, so Michael said I thought it was 2. Yeah, so 2 for standard deviation, 4 for variance. Anyway, that's beside the point. Just eyeballing it, we'd probably be roughly saying that they're pretty similar spreads, so it's probably reasonable that the variances are approximately equal. When I say that, that's we're testing, that's whether the variances in the population are equal. The variances of the samples will almost never be exactly equal, but because it's a sample. Okay, let's kind of continue on. So we looked at that assumption. The other thing to do is to look at a QQ plot. Oops, and I'll just... Okay, your standard QQ plot for the data that's combined looks like that. And you can use the QQ line function to actually draw the line in there, which makes it a bit easier. So that's for the complete data. But I found this thing called QQ plot, which is in the car package, that you have to load the car package. But look at this one, what this does, it puts these confidence intervals around the QQ plot. And so I feel a lot more confident saying that pretty much most of the points, there's just a few points here that are outside the confidence intervals. So I feel pretty happy about saying that these are within these confidence intervals, so they're lying along the line, so it's normal data. Now, something strange has happened here that, let me just check something weird. Why isn't the outlier showing up? Let me just make sure that I've got the right data file. Just want to check something. Oh yeah, no, it's right. So I don't know why it's not showing, but anyway, let's do that instead. But what I really want to do is, I don't want to look at the combined. I really want to look at the QQ plot for each group. Yeah, it could be the scale that we're not seeing it. But anyway, let's have a look at that, because that's what I did check. So we do the QQ. If we use this function here, I'm going to just do two side-by-side plots, and I want to do this way equals 1. See how that looks. Yeah, you can see what I did wrong there. Okay, that's good. So again, you can see it's starting to tail off here. So that's probably showing that, it's not purely normal, but, but it's not too bad. And here, yeah, it's all pretty normal, except this deadly outlier, which I put in artificially into the data set just to kind of illustrate this. Oops, too fast. Okay. So if we did a t-test, which we shouldn't do, okay, because of the outlier, the extreme outlier, I should say. It's not just an outlier, it's an extreme outlier. So if I did a t-test, well, I get a result, that's fine, and it tells me that my p-value is 0.03. It's still in below 0.05, so I would be rejecting the null hypothesis that the means are equal. So the difference there, they look pretty close from the box plots, at least the medians look close, but this t-test says that we can reject that. However, I wouldn't trust this result because it doesn't satisfy the assumption. So, that's not really to be trusted at all. But what do we get when we try it on the Wilcox test? Incidentally, what type of test am I doing? I'm testing here for difference, or that one is greater than the other. Am I testing that the smokers have lower birth weight than the non-smokers or not? Yep. Because I'm using the default options, I'm doing a two-sided test, so significantly different. And that's different to what was done in the notes, which was just testing whether one was a one-sided hypothesis testing one. But that doesn't matter, it's still a valid test to do. Okay, so Wilcox, what does that give? Okay, so the Wilcox gives me the Wilcox statistic, which is similar to the T statistic, but calculated differently. It gives me that number there, which doesn't mean much on its own unless you really know Wilcox test, but the key value here is the p-value. So it's saying 0.01. So it's actually giving me, I'm rejecting the null hypothesis even more likely, but that's a fair comparison. Yeah, it's not a fair comparison because the t-test shouldn't have been applied in this situation. So you can go back and if you like, yourself and try for that data set, but not the modified one I used, but the original data set on the smokers that was in week 4, where the t-test was run. You can try doing a Wilcox test and you'll find that, yeah, it gives you a p-value and probably still the same conclusion, but the p-value is less powerful. In other words, it's in that case, I think that it's going to be closer to 0.05. So it's not as guaranteed from memory. But anyway, if I had a lot of time, I'd do that, but I want to move on a bit. So what did I say? It was 0.01. Okay. I won't go through this. This is just, I could have tested whether they have higher birth rate using alternative grader, do a one-sided test. And I've sort of copied this from an example, so I just removed some. Yeah. I think this is, some you've got mixed up, and this is where I was doing that one, but I've already done it somewhere. Scrap that. That makes sense now. Keep it short and simple. Okay, so any kind of questions about that? Can I please repeat the two-sided question? The two-sided question for the non-parametric test is that the alternative hypothesis is that the medians are different. The null hypothesis is that the medians are the same. We rejected the null hypothesis, so we conclude that the medians are different. Steve asked, is there a minimum sample size that this works for? I can't remember. What does it say anything in the notes about assumptions of minimal sample sizes? I got a feeling there is, but I can't remember reading it in the notes. Yeah, we go. Yeah, I want to move to chi-squared now. I've spent, I meant to have only been half an hour on this. Yeah, that rings a bell, but I can't remember. Yeah, there might be a minimum size. So hopefully it's mentioned in the notes, but I didn't see it. But I haven't looked for it. So I'll have a look. Maybe ask this question on the discussion forum, and either me or one of the other tutors will answer that. Okay, so let's kind of go back to the slides, and I'll quickly go through the chi-squared test and then do some examples of the two chi-squared tests. Okay, so what do I want? I'll close the file. Okay. So yeah, I've should hang on. I've just hit. There should be a slide there saying chi-square tests. That's what it's showing on my screen. Okay. Yeah, okay, good. Okay, so let's move on to chi-square tests now. Chi-square tests are used for categorical data, and usually they're given as summaries of counts. So something like you might see like group 1, group 2, group 3. So this is where you have one categorical variable and you then have, say, various counts. The XX just refers to certain numbers. So one example might be, I might be working in a casino and I might want to test whether a dice is fair. And so I might have 6 groups then representing the 6 faces of the dice, and I might roll the dice, I don't know, 100 times, or maybe let's say 36 times, and then I count the number of times I get a 1, number of times I get a 2, number of times I get a 3, and so forth. And what this one's used for is to compare against a known or known proportions. So for a dice, if the dice was fair, I would expect to get the proportions of counts to be roughly 1/6 each time. If some other numbers have appeared more frequently than 1/6 and some less frequently than 1/6, then I'd be questioning whether the dice is fair or not. So that's kind of one example. There's another one in the notes, looked at, I think, conference attendees, and said what first the data was for the numbers of broken up into their vocations, their different jobs, and then there's some market research said that should be certain proportions, and so you'd be testing whether those proportions of your sample agree with what's known for the population. So what does this seem most similar to in terms of a t-test? Any ideas? It's not a t-test because it's yeah, not really, ANOVA. I know it's not exactly the same, but yeah, not a paired t-test. I'd say to me, it's most similar to a one sample t-test because a one sample t-test compares to a known mean. This one compares to a known probability distribution or known proportions. So that's where I see it as being similar or analogous. But of course, it's different because it's for different types of variables. It's for categorical type of response. Okay, the other type of test is called a chi-test of independence. And this is where I've got 2 variables. And again, I summarize the variables in counts. And so in each of the 4 groups here. So here, but we're not just restricted to 2 groups. We can have 5 groups in this one here and 3 groups in this one here. And what we're interested in doing is asking is whether this variable 1, is independent of variable 2, or are they associated? So they're the types of questions that you're asking. Now, that might be a bit abstract at the moment, so let's look at something a bit more specific. Here's a bit of theory that's not in the notes, and so you're not going to be quizzed on this, but the chi-squared test uses a test statistic, which is the sum over all the each observation minus each expected value. So if I've got like a known proportion, then I can work out what I would expect to get if I was rolling the dice 36 times. I would expect to get a 1 turning up 6 times. I expect to get a 2 turning up 6 times. It's the total times the probability. So it calculates this type of statistic called a chi-squared statistic, and it compares it basically to a chi-squared distribution with the appropriate degrees of freedom. So it just works in similar ways to what a t-test does, but So it's a different distribution. Okay, so that's just a little bit of a feel for what it's doing behind the scenes. The main assumptions are that most of the expected cell counts are greater than 5 and no cell counts are 0. So you must get something in every cell. What I mean by a cell is that's a cell, that's a cell, that's a cell, that's a cell, that's a cell. So our counts in each grouping here can't have any 0, and most of them should be bigger than 5. More than 80% should be greater than 5. So you don't want to be using this on really small data sets. The data have to be actual counts, and the categories can't overlap. And something that wasn't mentioned, but the sample data is randomly selected. Okay, so they're the kind of key assumptions. So now let's look at the goodness of fit test. So one categorical response variable. Compare it to a known distribution, and let's suppose I rolled a dice 60 times and I got the following data. And I'm asking the question, is the dice fair? And to put it into a proper research question is, are the proportions the same? So if I look at my sample data, I've got 10, 11, 12, 8, 9, and 10. Okay, they're not the same, but it's a sample, right? It looks similar. So, I mean, just eyeballing that data, do you think that that the dice is fair, that the same proportions? Okay, yes, fair. Yeah, most people think it looks pretty good. So we would do a hypothesis test. Yeah, David, will you post it? I always post my slide notes, so don't worry. Yeah, always. To what degree of confidence? Well, if we don't say, we assume 0.05. Yeah, is our cutoff. So, firstly, what are our hypotheses? That the dice is fair, and to translate it is that the proportions are all 1/6. And our alternative is that the dice is not fair. So, yeah, that's HO is the null hypothesis, correct? Just a shorthand notation for it. Sometimes people write H0, sometimes people write HO. Okay, so what would you be expecting to get without doing it for a p-value? Would you expect to get, looking at that data without doing anything else, thinking that the dice looks fair, what would you expect to get a p-value? Less than 0.05 or greater than 0.05? Yeah, so that's nice. A p-value that does not reject the null hypothesis, so greater than 0.05, correct. Yeah, I'm not really asking you what the p-value would be. Nobody can really tell that, but just, yeah, whether it would be small or large. So everyone's got good insight about that. Okay, so let's do that one in R. Oh, my R screen's gone again. Okay, hang on. Okay, just check that's there. Yep. Okay, just clean that up. It's not relevant anymore. And I'll clear everything, just as good practice to clear all the variables. Okay, so chi-squared tests. Okay, first one's the goodness of fit. They're just comments. And here's my dice example. And here I'm just inputting the data by hand. And I'm just gonna, just for tidiness, I'm just gonna give names to that data. So if I type observed down here in the screen, you can see here, for 1, I got 10, a count of 10, for 2, I got a count of 11, 3, I got a count of 12, and so forth. And I'm going to say what the probabilities are. So I just did that by using the rep function to repeat. I could have just typed it out as a vector, which is only 6. And just to show what that is, you see it's 1/6, 6 of them. So simplest use of the chi-squared test is I just say the observed data with these expected probabilities. There's various ways you can call the chi-squared. If you check the help, you can also tell it to, you can give it the expected numbers instead of the probabilities. But the most common way of doing it is where you give it the probabilities, because that's the way that's what you use the test for. Whoops, you wanted to do that. And so what do we get? Chi-squared test for given probabilities. Chi-squared is 32, so that was that that variable I wrote up before, the sum of the observed minus the expected over the expected, adding them up over all the data points, just as a matter of interest. It's calculated degrees of freedom of 5, which is 1 less than the 6 observations, so that kind of makes sense. And it's given me a p-value of, wow, that's small. I didn't expect that. I thought it would be bigger than 0.05. But anyway, so be it. It doesn't think that my dice is fair. See, I did everything right. Yeah, so what I should have got was this. So what did I do wrong? Let me just check I haven't made a mistake. Prov is correct. Yeah, so that's weird because when I ran it before, I got a p-value of 0.96. So I failed to reject H0. So just 1, 2, 3, 4, 5, 6. Anyone see I've done anything wrong? Hmm. It could be. Yeah, it could be. Yeah. So let me, yeah, that's a good point. But I thought I checked everything. So let me just go back and do it bit by bit. Yeah, have a look here in data. I've got data, which I don't have any data, but I'll clear everything. Okay, just do it one by one. Run. Don't really need that, but that's just for niceness. Now that's better. So well spotted. Yeah, when I hit the source, I've kind of overwritten the variable with something else rather than what I've just done. So that's much better. So I got, actually the chi-squared value was 1, degrees of freedom 5, the p-value is 0.96, so it's above 0.05, so I accept the null hypothesis. So sorry about that. It took a bit of time fixing that up. But anyway, so we conclude that it may be fair. If we had a suspicion that it was not fair, then we would need more data to be able to compare that, to conclude that it's not fair. In this case, it looked like it was fair. What I could do is I could just change these counts a fair bit and make that 25 instance, then run that, and Now I've got something that, yeah, it still thinks it's fair, but only 0.0. No, that's smaller. So now I would reject the null hypothesis and conclude it's not fair. George asked, is it that you accept the null or that you cannot reject the null? The correct answer is, the really strict correct answer is that you can't reject the null. But sometimes people say they retain the null hypothesis, but you shouldn't really say you accept it. What range of P would you say you need to do more analysis? But pretty much, yeah, normally anything bigger than 0.05 is not completely conclusive, but yeah, anything over your significance level, that's correct. That's strictly speaking. But in this case, so the way we write this is that based on the data that we have, there's no evidence that the dice is not fair. Okay, but that doesn't mean it's not. But it could be, like if you run 600 trials, maybe you might start to see it. But at least for those 10 trials, we couldn't really conclude that it wasn't fair. Okay, let's kind of move on so we don't go too far over time and talk about the chi-squared test of independence. So if you have two categorical variables, you're interested to see whether these variables are independent of each other. And so you basically summarize your data in what's known as a contingency table or a two-way table, if you've heard those terms before. So are they independent or do they have an association? So here's my example. Can't remember where I got it from, but this is a study of whether different types of nicotine devices have an effect on success of giving up smoking. So I've got two classes of people, those that are still smoking and those who have given up. So that's one categorical variable, a nominal variable. And then I have three different types of nicotine devices, nicotine gum, a nicotine patch, or a nicotine inhaler. So if we have a look at this, what looks like, the gum and the patch were, well, it's hard. To work out which is the more successful, we'd have to work out the proportions rather than just eyeballing the numbers. Okay, but what we can do is just do a chi-squared test on this directly. So the null hypothesis in this case is that the rows are independent. And in other words, that whether somebody's given up smoking or continuing doesn't depend on what type of treatment they've had. Okay, and the alternative hypothesis is that they are dependent. The success status depends on which method was used. So you can see the idea of what you're trying to test here. And I'll just pop over to the R file and show that one. I think I did lots of other cases, but anyway, let's go to this one here. Okay, so we got, basically what I've done is I've just made vectors out of each of the columns of my contingency table, gum, patch, and inhaler. And then I made a table and by using the cbind command, which binds the columns together, C for column, and bind them, kind of group them. So that makes a table. So there are my three columns, gum, patch, and inhaler, and then I just give labels. Row names gives label of smoke and given up. So I'll just do that, run. And if I have a look at data, I can look at it there. You see, here's my table. Now I've got to find where I put it. There it is. Okay, so all good so far. That's getting the data in. Now we can just do the chi-squared test. Okay, so here I get a chi-squared statistics. It's 3.06 something. R is calculated, the degrees of freedom to be 2. There's a formula for it, but anyway, yeah, it's not taught in the notes, so we just use R. And the p-value it's come up with is 0.2. So what can we conclude from that? We reject the null. Oh, sorry, yeah, we don't reject the null. We retain the null. So we can't reject the null, so therefore we would conclude that we fail to reject it, therefore the values are independent. They don't affect each other. So it doesn't matter what device you use, it doesn't affect your giving up or status of smoking. Okay. And if we were to reject, can you specify that question a bit more? If we were to, what will we do? If we were, okay. So basically you want to know what conclusion we would write if we happen to reject. Is that right? Yeah. What would be the next steps? Well, we don't reject, we fail to reject. So that's our conclusion from that data. Yeah, we might in practice we might collect more data, but I'm not necessarily that it would prove anything. I'd probably be, yeah. Okay, the name of the second test is the what's it called, the Bonferrari correction, but there's nothing similar for this. So we never accept the null hypothesis, but we do fail to reject it. So then we conclude something from that. We would then conclude that that those two variables are independent, and that the type of nicotine treatment doesn't appear to say whether people give up smoking or not. That's the kind of wording that you would use. Okay, so someone else might come along and repeat the test, and they might get different data, and they might get a different conclusion, but that's a conclusion for different data. Each p-value that you calculate is attached to your sample. So you always have to remember that you're looking for whether the sample provides evidence for you. It's not the probability of the hypothesis or anything like that. That's a pretty common mistake that a lot of experienced researchers make. It's just what it refers to, whether your data supports that null hypothesis or doesn't support it. Isabella asked, we test for alternative hypothesis if we reject the null. No, you don't do a second test. The test tells you that if you reject the null, you then tend to accept the alternative. If you fail to reject the null, then your conclusion is that you will conclude that your data supports the null hypothesis. Okay, so that was kind of the whirlwind tour of the non-parametric tests and the chi-squared tests. Give you a bit of an idea of what those are about, and some of you probably have read the notes already. Some of you are probably partway through the notes, but hopefully that kind of helps you a bit with some of that. George asked if it's not in the notes, it won't be tested. Does that include the readings that the notes refer to? I can't answer that because I can't remember. I think probably not. I'll have to go back and look at some of the original questions to see for sure, but I think, yeah, but I don't think it does you any harm to read the book, but Probably the notes are sufficient. Yeah, so that was right. The notes are a lot more detailed around the theory and the ideas. The book's more about, I think, how to use R to do things. Both have their purposes. So I think my answer is that probably isn't, but I'll do a bit of a check, and if it turns out that you do, I'll let you know. Otherwise, assume not. Okay, George. So I'm fairly sure there's nothing in the actual textbook. So there's nothing in the quiz that isn't in the notes. But I can't tell you for absolute certain without going back and looking at it. Yeah, I understand. I understand what you're saying. It's not You're not saying that you won't read the book. You're just saying when it comes to revising for the test, what you want to focus on. So I understand that. So anyway, but yeah, assume what I said was right, but I will check and I'll post something on the discussion forum if I'm wrong about that. Pretty sure that's correct. Okay, so no further questions. We might call it a night. Okay, so I'll just stop the recording now.